Hello, good morning to everybody, as usual, and here we are for our exercise session. I center a bit the blackboard. Okay. The larger the blackboard, the clearer the symbols and the better the lecture. So, this is a session about power series. Okay, power series will be, of course, object of the exam, and the typical problem of power series is the following. You have a series which is, for instance, this one, some real coefficient an, then the variable x to the nth power, and you want to find the radius of convergence, okay? Okay, because this power series, which is Taylor series of the Claudian series, converges in a neighborhood of zero, in a symmetric neighborhood of zero that can be given just by the point zero in extreme cases, and then the extremes of the neighborhood have to be studied separately, and the last part is about outside. Automatically, you know that outside the series does not converge. So it is very important to find this neighborhood, and R is exactly this width here. So this is the radius of convergence. Usual symbol is capital R. So we have that the series converges, uniformly and minus R. And then you have to check directly at points minus R what happens. So let us see it on some examples. So the first very easy example is the following. You have to find so the problem is find the set or the interval of convergence of this series sum for n going from 0 to infinity of x to the n power divided by n plus 2. Okay. You see, x to the n power, this reminds us of the geometric series, numerical geometric series you already studied, and I gave you some example in the past stringing lecture. So when x is in absolute value less than 1, this sequence of numbers goes down very quickly in such a way that the series converges. But if x is large, then this factor here becomes larger and larger. So you see that the width of x decided the convergence. So there are many methods to see what is the radius of convergence. There are basically two methods: the root criterion and the ratio criterion. This is probably useful to use the ratio criterion. So take this guy. This is an. So we have that an is 1 divided by n plus 2. And then the ratio is the limit. Sorry, the radius of convergence is the limit for n going to plus infinity of an divided by an plus 1. Provided that this limit exists. And in this case, this is equal to what? This is the limit for n going to plus infinity. An is 1 over n plus 2, so n plus 2 is at denominator. And at numerator we have n plus 1 plus 2, so n plus 3. This is a very easy limit, this is equal to 1. So the radius of convergence is equal to 1. Very easy computation. So once we have the radius of convergence, the information that we have is the following, is that here we have 0, and here we have an interval of length 2, which runs from -1 to 1. And the information we have up to now is that inside this interval there is uniform convergence of the series. Inside the interval, strictly inside. Outside the interval there is no convergence. It remains to decide what happens at the extremes. So the message I want to convey here, very important message, is that when dealing with power series, always recall that you have to check what happens at the extremes. Check directly. Okay, now we see it. So we have that the radius of convergence is equal to 1. So inside the interval there is convergence. Outside the interval there is no convergence. Let us check points -1 and 1 directly. There is no other methods. Okay, so the first step, see what happens in x equal to 1. So this function series, this power series, becomes a numerical series. So you have to discuss this guy here. Sum for n going from 0 to plus infinity of, instead of x, put here 1, divided by n plus 2. Now we already had exercises on numerical series. So here the result is that this series is exactly like the harmonic series. Indeed, this is nothing but the harmonic series. This is equal to n going by starting from 2. Because for n equal to 0, we have 1/2 and then 1/3 and so on. So this is n equal to 2 to plus infinity of 1 over n. This is the harmonic series. Not exactly, because there is no n equal to 1, but so if you are really want to be very precise, it is not necessary at all. We already know that it diverged, but this is the harmonic minus the first term of the harmonic, so -1. But the harmonic is infinite, is a divergent series. So here we have infinite -1, and this is equal to plus infinity. So we have that the point x equal to 1, the series diverges. So in our schema, here we have point 0, and then up to -1 we have convergence, up to +1 we have convergence, +1 must be excluded. Here we don't have anything. Here we have divergence. So the interval of convergence is open on the right. What about the left? We have to check it directly. no other methods. So I leave here this scheme and I cancel what we proved for the case x equal to 1, and now we analyze the case x equal to minus 1. For x equal to minus 1, we have to replace here variable x with a number minus 1. And the series, the resulting series is sum for n going from 0 to plus infinity of minus 1 to the n divided by n plus 2. Again, we already talked about this series made of terms with alternate signs that are infinitesimal because here the generic term goes to 0 as n goes to plus infinity and monotonically decreasing. If these three hypotheses, alternate sign, one positive, one negative, one positive, one negative, not two positive, one negative, three positive, six negative, one positive, one negative. So alternate sign, infinitesimality, the generic term goes to 0 as n goes to plus infinity. And third, the fact that the terms in absolute value are monotonically decreasing. Okay, these features altogether gives convergence. By Leibniz criterion. By Leibniz criterion. Okay, so here we have convergence. So at the end, the interval of convergence, I, is equal to close the interval at the left with minus 1 and open interval at the right, 1. Okay? Remember, first, through a limit procedure, which in general will be very simple, find the radius of convergence. Second, check the extreme points. And so let us go to another example that I want to clarify one point. Let us use here divided by n to the 5th power plus, I don't know, n squared plus 2. Why not? Okay. Again, to compute the convergence radio, you have to apply either the ratio criterion or the root criterion on this coefficient an, which is 1 divided by n to the 5th plus n to the square plus 2. And then you have to compute an divided by an plus 1. So you have 1 over n to the 5th power plus n to the 2nd power plus 2. And here you have to divide by 1 n plus 1 to the 5th power plus n plus 1 to the 2nd power plus 2. Let me write it again. I don't want to develop the 5th power. It is very long, boring, cumbersome, and it is useless. It is really not needed in order to solve the exercise. So we go here with n plus 1 to the 5th power plus n plus 1 to the 2nd power plus 2 divided by n5 plus n2 plus 2. Okay? Now, this is the ratio between two polynomials. Two polynomials of the same degree, which is 5. So when you perform the limit for n going to infinity, the limit is equal to the ratio of the coefficient of n to the 5th power here and n to the 5th power here. Simply limit of sequences, or if you want, limit of ratio of polynomials as x goes to plus infinity. So let me draw an arrow, which means that this guy tends to what? Here at the numerator there is 1. Here at the denominator there is 1, because the coefficient of n to the 5 here is 1. And the numerator there is 1, 2. Because when you develop n plus 1 to the 5th power, what you find is n to the 5th plus 4 n to plus 5 n to the 4th, and so on and so on. But what counts is only the coefficient of n to the 5th, so it is 1. So this limit exists, then the radius of convergence is again 1. Okay. Why did I do this computation? Because if you followed carefully the reasoning, it is easy then for you to recognize that whenever you have a polynomial here, or the inverse of a polynomial, the ratio criterion always will give you 1 as a result. The polynomial can be a numerator, nothing changes. You are led to a ratio of polynomials of the same degree with the same coefficient for the highest order term, a numerator and a denominator. Make whatever tries you want, if you don't grasp this argument. But the idea is that if you have in the more general setting, so this remark is very important because it may make you spare a lot of time when solving an exercise. When you have sum for n going to 0 from 0 or from other numbers to plus infinity of x to the n power, then times the ratio p over n divided q over n, when p and q are two polynomials, this is a polynomial, then the convergence radius is 1. This is quite impressive. I find this fact quite impressive because it may spare you a lot of time. So the message, so if you want to see a bit further, is that putting here a polynomial as a coefficient is not a modification that can change things in terms of radius of convergence. You have to put something strong. This is the main message. Okay, if you want to then to conclude this exercise, I leave you at home. Just replace points -1 and 1 here and look for the convergence of the numerical series. Okay, the final result, I cancel the remark and I just give you the final result. Final result here is that the convergence interval is -1, 1. This time it is closed both on the left and on the right. So check the extremes. This is the message. Let's check the extremes. This is the final result. Okay. So I told you, in order to move this guy here from 1, you need something more. You need something stronger than a polynomial. And you remember the scale of infinities or infinitesimal sequences that I gave you probably in the first lecture of numerical series. Polynomials are quite fast to infinity, but exponentials are much faster. So let us look what happens when we add an exponential. And so we go to the third example of this lecture. The third example of this lecture is the following. Again, the exercise is always the same. Find the interval of convergence of this guy here. Sum for n going from 0, plus infinity. Let us remember the first exercise. We had n plus 2 at the denominator, but then here we add 2 to the nth power. Here we add another factor, which has an exponential form. And this time we use the ratio criteria, the root criterion. Why not? The other root criterion is the following. Consider, so an, in this case, is 1 divided 2 to the n plus 2. Consider, instead of the ratio of an divided by n plus 1, consider an absolute value, and then the nth square root, or if you prefer, an absolute value to the power 1 over n. Okay, in our case, this is 1 over 2 to the n plus 2 to the power, everything to the power 1 over n. 1 is insensitive to any power. 2 to the n power 1 over n is just 1 over 2. And here you have 1 divided by n squared of n plus 2. 1 over 2 is a factor. And now you have to remember from analysis 1 that when you have the nth square root of every polynomial in n, the limit is 1 for n going to infinity. So the limit here is 1/2 times 1. And now a theorem says that the radius of convergence is the inverse of the limit of this guy here. So we have that, in this case, capital R is equal to 2. So adding a power here to the n was able to move our interval of convergence. No longer an interval of convergence of width 2, but this time is of width 4. Why? Because now the interval of convergence, let me cancel here an. Again, start from 0, and then we go plus 1, here, plus 2, here minus 2. And again, you may be interested in asking what happens at the extremes, and what happens at the extremes now, okay, must be computed very case by case, as usual. So let me do it without speaking too much, and you will immediately recognize what happens. So let us start from x equal to 2. For x equal to 2, what you have here is, so let me write the more complete way. For x equal to 2, you have to evaluate this series, sum for n going from 0 to plus infinity. Here you have 2 to the n, divided 2 to the n, n plus 2. So these two cancel. So you are led to the series 1 divided by n plus 2. I already met here in the first exercise of today, and this is nothing but the harmonic series without the first term, so this diverges positive. On the other hand, the same computation for x equal to minus 2, then you have sum of minus 1 to the n divided n plus 2. And by Leibniz, this is a convergent series. This is Leibniz. So, as a final result, we have that here convergence and here divergence, and so the interval I of convergence of this series is, sorry, it's closed here, minus 2, 2. Very simple. Notice that this series moves the interval of convergence, so it magnifies by 2 the interval of convergence of the first series. So we can immediately verify it in a very direct way. And this is the way we are doing it. So let us start from our series, our last series, and from 0 to infinity of x to the nth power divided by 2 to the nth power n plus 2. You can write it like sum n from 0 to plus infinity of new variable y to the nth power divided by n plus 2, where we introduce the variable y equal to x over 2. Now, according to our study in the first exercise, the convergence interval in y, so converges if and only if y belongs, or let me say, minus 1 is less but also equal by Leibniz to y less or equal to 1. Sorry, not equal, only less. There is no Leibniz here. So this is exactly how saying that minus 1 less or equal x divided by 2. So minus 2 less or equal x less than 2. So here you can really try to understand why adding an exponential gives you this shrink, or on the other hand, this magnification of the interval of convergence. This is just like that. Okay, we are exactly in half an hour. This was my program of my first lecture on function series, and we will have another one later. Thank you.